Hello and welcome into the Everyday Strength Podcast. I'm your host, Anthony Hagley. In today's episode, we're talking all about advanced strength training techniques, but not in the usual sense of exercises or programs, not squats versus deadlifts, and not sets and reps, but more from a physiological standpoint. The more interesting variable is not the movement itself, but it's how force is distributed across that movement. So talking about straight weight, bands, chains, and partial ranges are not different philosophies of training, but instead different ways of shaping the external force curve relative to the internal strength curve of the athlete. And this episode is about understanding that relationship. So the natural place to start is the simplest case, straight weight. And simply put, this is weight on a bar. So the barbell imposes a constant external load, right? 200 pounds is 200 pounds at the bottom, in the middle, and at the top of the lift. The implement itself does not change, but instead the external resistance is fixed. But the body does not experience that load the same way throughout the entirety of the movement. As joint angles change, moment arms change, as muscles shorten or lengthen, their capacity to generate force changes as well. And as leverage improves, torque production also improves. So even though the external load is constant, the internal demands placed on the system are continuously shifting. And this is fundamentally a mechanical problem, right? Force production is constrained by geometry. The length-tension relationship determines how much force a muscle can produce at a given length, and joint structure determines how efficiently that force is transmitted into movement. And moment arms determine how much torque is required at different points in a lift. In most compound movements, those factors tend to align in a similar way. You are mechanically disadvantaged in the deepest positions of a movement, where your joint angles are compressed and your leverage is poor. But as you move throughout that range of motion, then your leverage improves. Moment arms change, and that same external load then requires progressively less internal effort. So in a squat, in a press, or a deadlift, right, your force capacity generally increases as you approach lockout. We've all experienced this. The bottom position demands the highest relative effort. Those top positions allow for much greater force expression at the same absolute load. Now, this isn't an inherent training flaw. It's just simply how human joints and our muscles are built. And the important element here is not that one part of the lift is hard and another is easy. The important point is that the same external resistance produces very different internal demands depending on joint position, which means that at every loading strategy, whether you realize it or not, it is implicitly answering one question: where in the range of motion do I want to emphasize force? The barbell answers that question in one very specific way. Other tools can answer it differently. And once you begin to look at training through that lens, then you stop thinking in terms of exercises and you start thinking in terms of your force distribution. Because ultimately, what this really introduces is the idea that the strength itself is not a single number. Strength isn't just how much weight is on the bar, but it's about how much force the body can express at different positions within a movement. So this is where the concept of the strength curve becomes useful. The strength curve describes how much force you're able to express at each point throughout a movement. Not in a theoretical sense, but mechanically. At every single joint angle, there is a maximum amount of force that you're capable of producing under the constraints of muscle length, leverage, and neural drive. In some lifts, force capacity increases as the movement progresses, and these are often described as an ascending strength curve. So think squats, presses, deadlifts. They generally fall into this category. The bottom positions are the most mechanically demanding, and as you start to approach lockout, leverage can improve and force expression can increase. Now, in other movements, the pattern is a bit more complex, and some have a relatively flat curve, and some even have a descending curve. And many ultimately depend heavily on joint structure and technique and the individual anthropometrics. So think about two people performing the same lift. They can have meaningfully different strength curves based on how long their limbs are, different segment ratios, or even the bar path of their barbell through that movement. But the underlying principle remains the same, and that is that your capacity to express force is not uniform across a range of motion. A lot of times people will refer to this as a sticking point, and that's simply a location where the external load now exceeds the internal force that you can produce at that specific joint. It's not a mysterious failure mechanism, but it's that point where the curves cross. And importantly, that crossing point isn't fixed. Strength curves aren't static features of the body. They can adapt. So if you expose a joint angle to a higher force demand, then force capacity at that angle can start to increase. Right? If certain regions of the movement are consistently underloaded, then they can tend to remain more underdeveloped relative to others. So when we talk about strength curves, we're not talking about identifying weaknesses, but we're talking about describing how geometry can shape force expression and how training can reshape that geometry over time. Now, once you start thinking about it this way, then the obvious next question becomes, how do different loading strategies actually interact with that strength curve? In other words, what kind of force distribution does straight weight by itself create? Straight weight is extremely effective at developing force in mechanically disadvantaged positions because it emphasizes force in those portions of the movement. This is the bottom of a squat, off the chest in a bench press, from the floor in a deadlift. Okay, those are the positions where leverage is poorest and moment arms are longest, and the internal effort is highest relative to the external load. Straight weight forces the system to produce higher force under these more unfavorable mechanical conditions. And that's why straight weight is such a powerful developmental tool. It builds robustness and deep joint angles, and it improves the coordination when leverage is limited. And from there, it can develop the ability to produce force in positions where small technical errors can carry large mechanical consequences. So in other words, straight weight is very good at teaching the body to generate force where our geometry is working against you. Now, by definition, it also underloads those mechanically advantaged positions, right? As you move through a range of motion and your leverage begins to improve, then the external load remains constant while that internal force capacity increases. Near lockout, you are often capable of producing far more force than the bar is actually demanding of you, right? The limiting factor is no longer force production. It's simply completing the movement, right? The result is that large portions of the lift, particularly in strong joint angles, are not being maximally loaded. They're exposed to movement, but not necessarily to the peak forces. Again, this isn't a problem. It's just that's a property of the system, right? Straight weight expresses a very specific force distribution. We take high relative stress in weak positions. Straight weight expresses a very specific force distribution, right? High quality, high relative stress in weak positions and progressively lower relative stress in those strong positions. That's also why straight weight truly remains the foundation of almost all strength training. It's simple, it's stable, it's scalable, and it reliably exposes those most mechanically challenging parts of a movement to be meaningfully loaded. But it also means that straight weight is not a neutral tool, right? It prioritizes certain regions of the range of motion, and it can deprioritize others. So it doesn't train strength in an abstract, right? It trains a particular pattern of force expression. And once you see straight weight as one possible way of distributing force, then the obvious next question becomes, what happens if we intentionally reshape that distribution? What if external load increases as internal capacity increases? And this is where accommodating resistance starts to come into play. Okay, accommodating resistance, think bands, think chains, that changes that force distribution. Bands and chains increase the external load as the lifter becomes mechanically stronger. So as you're extending the joints and as you're improving leverage, the external resistance also increases. So instead of the bar staying constant while internal force capacity rises, the external load rises right alongside it. The force curve of the implement begins to resemble the force curve of the body. So in other words, external forces increases as internal force capacity increases. And this is truly like the defining feature, right? You're no longer working with a fixed external load, but instead you're working with a variable load that responds to joint position. The practical implication is that higher forces can be expressed in those mechanically advantaged ranges without requiring maximal straight weight. Now you can expose strong joint angles to meaningfully force without having to overload those weakest positions of the lift. And that changes the internal stimulus, right? You get this high force expression where the system is normally underloaded without necessarily increasing the absolute load or joint stresses at the bottom of the movement. So mechanically, bands and chains achieve this in slightly different ways. Bands can produce a continuous increase in tension across an entire range of motion. So the further that you move from the anchor point of the band, then the greater the elastic resistance becomes. The force curve with this is very smooth and it's very progressive. Now, chains, on the other hand, they produce a stepwise increase in load. So as more chain links leave the floor, then the effective bar weight increases in discrete increments. The curve is less smooth, but it's still position dependent. In both cases, the common feature is that external load is no longer constant, but it is position sensitive. So from a neural standpoint, this often increases our motor unit recruitment in strong joint angles that would otherwise be relatively underloaded with straight weight. The system is required to sustain those high force outputs through a larger portion of the movement. And so from a programming standpoint, this allows for high intent and high force exposure with more control over your fatigue. So you can now maintain aggressive force production without relying solely on maximal absolute loads. And importantly, the key point is not that accommodating resistance is better. The key point is that it can reshape where force is emphasized throughout a range of motion. Straight weight concentrates force demand in weaker positions, whereas accommodating resistance allows you to redistribute that force demand towards your stronger positions. Both are very legitimate, but they simply solve different mechanical problems. All right, so far we've been talking about reshaping the force curve across the entire movement. But there's another way that we can manipulate our force distribution, which is not by changing the implement, adding bands and chains, but by changing the range of motion itself. And this is where partial range of motion training comes into play. So partial range training does something differently. Instead of reshaping the external curve across the entire movement, instead it isolates specific joint angles. So here we're going to think about movements like the box squat, pin presses, rack pulls, Anderson variations. These are Tools that allow you to concentrate force exposure in a defined region of the range of motion. So rather than asking, how does force change across the lift, partials are going to ask, where in the lift do I want force to be concentrated? Now, from a physiological standpoint, this matters because strength is highly position specific. Your neural drive, your coordination, your ability to express force, those all adapt at specific joint angles. So the nervous system learns to produce force in the positions that it is exposed to, right? If a joint angle is consistently underloaded, then the system has little reason to increase its force producing capacity there. If a joint angle is repeatedly exposed to high force demands, then the system can adapt accordingly. So partial ranges aren't shortcuts through a movement, but instead they're about avoiding the difficulty, right? They're about deliberately selecting where difficulty occurs. They allow you to overload the force production in regions that may never truly see maximal demand during full range of motion training. And that can be true at the bottom of a lift, the middle, or near lockout, depending on how that partial is structured. And this also has important implications for your fatigue levels, right? Because partial ranges reduce total movement distance. They often allow you to be exposed to high force with lower total volume and lower systemic cost. So now you can generate significant neural and mechanical stimulus without accumulating the same excessive metabolic or structural fatigue as that full range of motion. This is why partials are useful not only for maximal strength development, but also for fatigue management, right? They allow you to maintain high force output while controlling how much total stress you're imposing on the system. So this isn't just about weak points, right? Weak spots in the lift. It's about constraint, isolation. It's about choosing a joint angle and saying, this is where force expression will be trained. So now at this point, we've looked at three fundamentally different ways of distributing force. We've got fixed external load, reshaped external load, and targeted joint angles. So now the real question is not which one is best, but instead how these tools can fit different training contexts. So we don't want to think about this as which method is best, but what constraints am I working within? This is programming 101, right? So far, we've talked about loading strategies in abstract terms, thinking about fixed external load, reshaped external load, targeted joint angles. All of those are design tools, but none of them exist in a vacuum, right? They only make sense relative to the constraints and the training environment of the athlete. Different athletes are not different because they need different philosophies, but they're different because they operate under different constraint sets. So powerlifters, they're constrained by competition specificity. They need to be able to produce maximal force at very specific joint angles under maximal external load. The task here is narrowly defined and the outcomes are unambiguous. So for powerlifters, reshaping the force curve and targeting those specific joint angles can make sense. Accommodating resistance can help expose those strong ranges to a higher force, and partial ranges can concentrate adaptation at known bottlenecks. Now, the loading strategy here is engineered around a very precise performance demand. Next, we've got hybrid athletes, and they're constrained by their ability to recover. Right? They need to express high levels of force, but they also need to preserve their capacity for work through endurance. Right? Their problem is not how to maximize force production at all costs, but instead it's how to maintain their force expression while managing their total systemic stress. So for them, reshaping the force curve becomes a way of increasing stimulus efficiency. You can get meaningful force exposure without relying exclusively on maximal straight weight. Partial ranges, they become a way of maintaining high neural output while controlling total volume and fatigue. Now, field sport athletes, they're constrained by transfer, right? They don't just need force, but they need force that integrates with speed, with conditioning, with coordination, and sport-specific movement patterns. Strength is truly only useful to the extent that it expresses itself within the demands of the sport they're participating in. So for them, these tools are more supplemental, right? They can support force development, but they can't truly replace full range, high coordination movements. So with them, the loading strategy has to, truly respect the movement ecology of their sport. Time constraint lifters now are constrained by volume. They have they don't have unlimited time for sessions or recovery bandwidth, so they need efficient stimulus with minimal noise. And so for them, smarter force distribution becomes a way of maintaining their strength with less total work. Reshaping and targeting allow force exposure to stay high when total training time is low. And this is really that core idea. So now these are not different populations requiring different philosophies, but instead they are different constraint sets requiring different loading solutions. The methods don't change, the system they're applied to does. So if you zoom out from everything we've talked about, the pattern starts to become more clear. And that is that strength training is not really about choosing the right exercises. Instead, it's about choosing how and where force is expressed. I view exercises as containers, right? Squats, presses, pulls, carries. They give structure to movement, but real training signal comes from how force is distributed within those movements. So straight weight, accommodating resistance, partial ranges, they're not competing methods, but instead they are design variables that we can implement and modify in a system that's governed by your biology. So there's different ways of mapping external load onto internal force capacity. And once you begin to start thinking in those terms, then training becomes, less about collecting these different methods and instead starts to be more about engineering exposure. We're no longer asking, what should I add? But instead, what kind of force expression does this truly create? And that's what separates these advanced training techniques from basic training techniques. It's not just complexity. It's not novelty, not more tools in the toolbox, but instead precision. Advanced training isn't more complex. Instead, it should be more precise. And the more precisely that you understand that force curve, then the less random your programming becomes. So thanks for listening to the Everyday Strength Podcast. If today's episode helped you learn something, do me a favor and make sure you're subscribed on YouTube, Apple Podcast, or Spotify. This helps the show grow and it ensures that you never miss an episode. If you're on YouTube, drop a comment. I read all of them. And if you're on Apple or Spotify, then a quick 5-star review goes a long way in pushing this information to more people. If you want to go deeper, then join the Performance Edge Network. It's free to join and it gets you access to my weekly newsletter, which is full of training breakdowns, physiology deep dives, and tools that you can apply immediately to become a stronger, fitter, higher performing everyday athlete. And if you're ready for structured programming, then I've got options for whatever path you're on. The Peak Performance Training Program is my flagship strength and conditioning program. And I also offer Peak 3X, which is a 3-day per week version for busier athletes, along with other programs designed for hybrid competitors, runners, and anyone who wants to train like an athlete year-round. You can find all those and more at HaleyStrength.com. I appreciate you being here. Keep training hard, and I'll see you in the next episode.